So in the previous video, the main conclusion was that turbulence is chaotic. And towards the end, I mentioned that this kind of meant that we can only talk about statistics. So that's the line of thought that I would like to proceed in this video. So that's going to be about what can we predict about turbulence. And we see that there's actually, I want to talk about two different things in terms of what we can predict. And I'll do those in two different videos. The first one is going to be about the bulk behavior of the flow, and the second one is going to be about what happens specifically around the object, so in the boundary layer, around the boundary conditions. So first, the bulk behavior of the flow. And I talked about mean flows and root mean square, so that's not yet specifically what I mean. That's not specifically what I want to talk about. I want to talk about more physically inspired statistical behavior of turbulent flow. And it's going to have to do with number 3 and number 4 of the list here. It's going to have to do with that the flow is going to mix momentum, and the 3D behavior had to do with this stretching of vortices. And what those two things going to end up doing is produce a certain distribution of kinetic energy across various length scales. And that is a very characteristic behavior of turbulence, that it produces, out of all the chaos, it produces a predictable distribution of energy over different length scales. Now, to kind of motivate that from a slightly more familiar perspective, I want to talk about two linear partial differential equations that, if we combine the two, kind of do something similar. And those, that's the motivation to the Burgers equation. The Burgers equation I talked about a couple of times, although that's a nonlinear equation. But we can think about the Burgers equation as a combination between a parabolic equation and, well, actually a nonlinear hyperbolic equation. So I'm sorry, I shouldn't say two linear equations, but two simple equations. Let's put it that way. So we have a parabolic equation right here. That's our heat equation, time derivative, and a diffusion term with a certain parameter up front. And if we have a certain initial condition as a certain wave, as you're seeing right here on the left, and I'm using here a periodic domain, so that means that you can think about the solution field as living on a ring. So the value at 0 is going to equal the value at 6. And if we then continue in time, then we see that our solution is being smoothed out. And that's what the heat equation is doing. It's smoothing things. That's why it's a very stable partial differential equation. So can we be a little bit more specific rather than just saying that it smooths things out? Well, we can look at the energy distribution. And that's the plot that I will try and show for different equations a couple of times. Now that's the one on the right, the energy spectra, where we have as our y, on our y-axis an energy per mode, and on the x-axis we have the wave number. So how did I obtain a graph like this? Well, I took the Fourier series. I took the Fourier series of the solution fields on the left. And for each mode in the Fourier series, I can obtain the energy that it captures. It's actually more simpler than what it sounds like. I think you simply have to take the square of the Fourier the Fourier coefficient. That ends up having the units of energy, and it has the same characteristics of energy in terms that if you sum all the squares, you end up with the total energy. And so that's what we're trying to plot here. We're trying to plot how the energy distributes itself over all different length scales. Now we can think about the different wave numbers as different length scales, in the sense that low wave numbers show very spread out behavior, large length scales, whereas small wave numbers are very oscillatory, have a very small length scale. And if we then track the behavior in that energy spectrum plot over time, then we see that the energy is distributed in time homogeneously over our, it actually is being transferred to the higher energy mode, or the higher length length characteristic modes, so the lower wave number modes, or stated differently, the high wave numbers are being dissipated. And that's kind of the point that I'm trying to make here. So we have in the black line again the initial condition, which is a relatively homogeneous distribution of the energy, and as time progresses, the energy in the high wave numbers, the small length scales, is being pushed down. I think that's the way that we can interpret this graph. So that is the behavior of diffusion. That kind of makes sense as well with our interpretation of it being smoothing. If we have a certain step or a certain shock or a certain high oscillatory behavior, well, that is getting smoothed out very quickly. And that's step becomes a smooth bump very quickly. And that's because these high wave numbers that have to do with characteristics like steps, they're being dissipated. So the nonlinear hyperbolic part of the Burgers equation and the Navier-Stokes equation has a very opposite effect. So here we have a nonlinear hyperbolic equation. We have still our time derivative of u. We have now a first derivative, which was an advective term, and our advective velocity is actually the field itself, right? So we have an advection equation in a nonlinear sense, a nonlinear hyperbolic equation. So on the left we see how the same initial condition is going to behave as time progresses, and we see that this actually tends towards a step function. It's starting relatively smoothly, and it's as time progresses we get a shock. And if we then look at the behavior of the energy spectrum, then we see that we have pretty much the opposite effect compared to the parabolic equation, where we had the high wave number, the small length scale modes that was dissipated. We actually see that energy is being pushed to those high wave number, the small length scale modes. So where again in the initial condition we have the black line, we see that as time progresses, energy is slowly pushed towards these high frequency modes. So now the interesting thing is what's going to happen if we combine these two, because, well, that's precisely what the Navier-Stokes equations are. They are a nonlinear hyperbolic part, a nonlinear advective part, in combination with a diffusion term. So that's also precisely what the Burgers equation is. And here I have now a video where, let me just restart this. We start with a flat initial condition, and then I have a certain body force that's going to introduce a wave motion. And then we see how this nonlinear hyperbolic term and the diffusive term try to fight one another. So it's starting to look like a shock, because that's what the nonlinear hyperbolic part is trying to do. But it doesn't become a pure shock. There's still a certain diffusion at play as well that tries to smooth it out. And so we don't get a pure discontinuity. We have if you zoom in, you see that there's a very small smoothing of that discontinuity. And if we then look at the energy spectrum, then we also see that it's precisely a combination of the parabolic equation and the hyperbolic nonlinear equation, where the parabolic equation is trying to push down the energy at the high frequencies. That's the diffusion, and whereas the hyperbolic equation is trying to push the energy to these high frequencies. And as time progresses, this finds a certain balance where we see this distribution of energy as such. Now this is what you're seeing right here is actually already something I want to talk about later, so forget about this one for now. So this is the Burgers equation, and it's made up of two relatively simple partial differential equations, and the Navier-Stokes equations are significantly more complex. But still, we can actually find very similar behavior in the energy distribution for the full Navier-Stokes equations. And I first want to show that with a couple of pictures. I think this one we saw already before, where we have these eddies in the beginning, and these eddies, which are large length scale characteristics, and they break apart and they start to mix, and they transition into very small length scale characteristics of the flow. And that's precisely this this effect of the nonlinear hyperbolic equation. And yeah, you see that as well over here, where you get this breakup of larger structures into smaller structures. And that was again also what this 3D characteristics of the flow did, right? This vortex stretching that has to do with this as well. And at the limit case, you get, so these are the energy spectra that we would obtain for the fluid motion in Navier-Stokes equations. And it looks a lot like what we just saw for the Burgers equation, where we have at the very high frequency modes, the high wave number modes, the small length scales, we see a sharp drop-off. That's what the diffusion term is doing. But the nonlinear advective term is actually transporting energy to those modes. And this is something that was studied already quite a while back by a statistician called Kolmogorov. And he actually found that with a certain number of very mild assumptions, 2 or 3, he could find that he perfectly predict this behavior. So on the right we see actual measurements of different simulations, and on the left we have a certain prediction according to the statistical behavior, where Kolmogorov also determined that the slope of this energy transfer from large scales to small scales should be -5/3, and that has since been verified by experiments. So it's interesting that an equation that produces such chaotic behavior still also at its core has something that is predictable with a certain funny constant of 5/3. Now, a course on turbulence would go into this at a much higher depth. What I want to focus on, though, is that we want to sort of mimic this type of behavior if we want to model fluid flow, turbulent flow at high Reynolds numbers. And the physics that we are observing with these plots and from these figures is that energy is being transported from high large length scales to small length scales where it is being diffused. And that's precisely what we should take into account in our numerical simulations. So these graphs, they also happen at different Reynolds numbers, as we're illustrating right here. Naturally, for low Reynolds number, we don't really have turbulent flow. It only becomes turbulent at certain length scales. And that's kind of what we're seeing here, is that graph starts to develop and has a larger region where this 5/3 holds as the Reynolds number increases. Okay, and here we see what you would, well, as we try to zoom into those different length scales, so we try to traverse the graph. I have here a couple of pictures where you see the different behaviors of the flow. As we zoom in, we see that this energy is being captured in finer and finer flow structures. And yeah, so I think one of the main mechanisms that is causing this is this vortex stretching, right? This where large eddies stretch around their perpendicular axis, become thinner and speed up. Well, that's precisely the mechanism behind this energy transfer from large length scales to small length scales. And again, that is a fundamentally 3D property, so that only happens if we talk about turbulence in 3D cases. And in that sense, coming back to the example of an airfoil, if you were to perform a 2D simulation of an airfoil and try to model turbulence, you're not really modeling an airfoil. You will be modeling an airfoil shaped island in a lake or in the ocean, right? So that's I think is a very clear reason for why you don't want to do that. We can think of the ocean as also 2D flow. So that is what you will be modeling rather than actual airflow around a wing. Okay. Yeah, so one of the assumptions that Kolmogorov had to make in order to come up with this model that ended up working remarkably well is that at the smaller length scales, so that would be around here, you would have something called isotropic turbulence. That means that there's no clear orientation of flow anymore, right? So if we zoom out, we see that flow is moving from left to right, but if we zoom in, if we move with this mean flow, you should get something that is isotropic, the same in every direction, and that is something that kind of shows here as well. This is what we call isotropic turbulence. Okay, so now it's finally time to start talking about modeling. And if we talk about modeling of turbulent flow, then there's really three different pathways that we should discuss. These are DNS, LES, and RANS. So these are three different simulations of the same physical system, the one on the left. And these three different simulation methods, they also vary from left to right in terms of computational expense. And inversely also in terms of computational fidelity, the detailedness of the simulation. So DNS means direct numerical simulation. This is impossibly expensive for relevant scenarios. This is the case where you try to you refine up until the point that you're capturing all the length scales in the complete curve of the graph. And so maybe at this point I should actually also point out that this graph has an end. That is over here. This is where the energy is dissipated in terms of in between molecules in terms of heat. That is the final level of the graph, and that is the Kolmogorov length scales are here. So Kolmogorov developed this graph, and the scales corresponding. Oh, sorry, I'm not showing the mouse at the correct location. The scales corresponding with this cutoff of the graph are called the Kolmogorov scales. So that is where energy is dissipated in terms of heat. And that is also the smallest scale that we would have to take into account if we want to do a full-scale model of our simulation. And that is what DNS is trying to do. Direct numerical simulation. It's trying to refine up until the level of the Kolmogorov scales. So we take into account all scales of the simulation. And in that sense, there is no assumption, there is no need for modeling. Now, this is, again, too expensive for any real-world application. Yeah? I think we can do this for small boxes in order to understand statistical behavior of turbulence, but we're not even able to do that on small boxes for high Reynolds numbers, so it have to be small boxes and small Reynolds numbers. So I'm not sure if the simulation that I'm showing here is actually doing DNS in the sense that it would take into account all scales of the physics here on the left. I would doubt it, but I don't actually remember where I have this from. But that's the basic idea. From direct numerical simulation, you refine to the level that you take into account all scales, and you would be able to get the complete energy distribution graph as Kolmogorov predicted. Now, that's too expensive. So what are we going to do instead? Well, we can either do LES or RANS. And LES is actually still quite expensive, but this is what most of the computational research is about, because we're getting to a point where we have sufficient computational strength that we can do a little better than RANS, which we'll get to in a second, and we can take into account a bit more of the detail of the flow, and that's what LES is trying to do. So we're not trying to compute the complete flow field and every detail of it, but we're trying to compute a filtered flow field. We're trying to compute only the larger length scales. So again, on a class which focused on turbulence modeling, we would go into this in detail. But the idea is that you perform a certain filtering operation on the true DNS solution field, which may either be a Gaussian filter with a certain length scale or a top hat filter or whatever. So some averaging around a certain region. And if you would do that, if you would perform that filtering operation, then you would get a a less detailed flow field, right? You would get a smoothed out flow field, but the objective of LES is then to not compute the true solution, but rather to compute this filtered solution. So conceptually what we're doing here is we're trying to compute only the larger modes in that graph. And in order to do that, you would have to take into account the effect of everything that you're cutting off. And that is precisely what a turbulence model would be. It would be to try to take into account the effect of the small scales on the large scales. And that's hence why turbulence modeling and multiscale modeling really is one and the same thing. So then what is RANS? Well, RANS is a much older technique, Reynolds average Navier-Stokes. Osborne Reynolds already proposed a rewrite and a manipulation of the Navier-Stokes equations that is at the core of what we're trying to compute here in RANS. It is not quite as simple as what I'm going to say right now, but you can think of this as trying to compute the time average of your solution. So you would take the average of the solution across many time steps, and that is the solution that you want to obtain. So the way that you would obtain the RANS equations would be to take the Navier-Stokes equations and average those over time. Because they're nonlinear, they don't quite end up being quite so simple. If you would have a linear equation, you could do that. You could average the equation over time. You would just pop up time average solutions everywhere. But due to the nonlinearity, you get certain cross terms, certain terms that involve also this mean solution that you're trying to obtain, but multiplied with a fluctuation. And then the RANS models, and there's a wide scala of turbulence models for RANS, those are the models that would try to determine or model the impact of the fluctuations on the mean. So if we look at all these different modeling techniques from the perspective of this energy cascade graph, and then we can think of them like this, where we have on the left what we're trying to resolve with our computation, and on the right what we're not resolving, and thus what we have to model. And then, well, for the DNS, the direct numerical simulation, well, we're not modeling anything, we're resolving everything. That's typically way too expensive. On the other side, we have RANS, where we're not resolving anything, we're just trying to compute a mean. And that means that we have to model all the fluctuations onto that mean, so we have to model everything. And LES is sort of a balance between the two, where we're trying to resolve the larger length scales, the lower frequencies. So you would try to resolve a fraction of that graph, which means that for your model you would have to take into account everything that you're not resolving, and that is, well, whatever is left. So how do we model things like these? Well, we talked about that turbulence, and specifically these smaller length scales, they mix and they diffuse. So a lot of these RANS and LES models, they try to replace the effect of all the fine scales by diffusions. Now that is a variationally inconsistent model because it's eddy viscosity models. We talked about variational consistency quite a bit before. What you want to do is you want to make sure that your numerical method is, or the equations that you're solving with your numerical method, that those equations are actually satisfied by the true solution. If you simply add an eddy viscosity on top of your equations, well, then the true solution does not satisfy that. So those are variationally inconsistent models. And what we'll do in the next few videos is we're going to develop variationally consistent models. The reason why we can do that is because we're using a finite element method. And maybe I'm being too rigorous here. But all these models from RANS and LES, they have been proposed in the finite volume community already decades ago. And they're still being developed. But in the finite element method, because we're dealing with certain function spaces and approximation spaces as being subset of function spaces, we can do something that is a bit more mathematically rigorous, and we can have a certain very clear definition of a separation of scales, and these definitions of separation of scales is not quite so clean for the finite volume take on RANS and LES, and by doing so we can actually get variationally consistent turbulence models. But I'm getting ahead of myself. What I want to show here is just the different flavors of computations that you would see, and how they relate to the physics, right? How they relate to the energy cascade. So this is to kind of as the last slide in this video here. Again, the simulation of the road sign that we talked about in the previous video. And this is precisely what I was just talking about, that we use a finite element method where I have a very clear definition of variation of the separation of scales. I use this slide quite often to motivate this the energy cascade. So if we zoom into our sign structure here, then we see that we have a pretty heavily refined mesh, but even within the elements, we have very detailed flow behavior, and I can zoom in much further than that, 2 times, well, a factor of 20 and a factor of 50, and only after we zoom into those factors, which ends up being 1,000. But you have to think of this as 1,000 in one length direction, right? So if you were to refine, you would need 1,000 cubed, and only then do we get to the smallest length scales. Those are the Kolmogorov scales. That is where, again, we get the diffusion, the molecular diffusion of the kinetic energy to heat. And that's the smallest length scale. That's where the energy cascade graph drops off. So a model would try to not take into account all these length scales. That would be direct numerical simulation. That would be too expensive. But rather be trying to compute the core scales up until this level, while taking into account the fine scales by means of a turbulence model. And the method that we'll discuss quite extensively is the variation of multiscale method. So in between here, I'm zooming into an element that is on the boundary layer, and we also see some interesting behavior of the fluid at this boundary layer. There's also certain statistical behavior that is predictable in the boundary layer, and that is what we'll first talk about in the next video. And only after that we're going to talk about the variation of multiscale method and how we would use all this acquired knowledge in terms of physical behavior of fluid in our numerical setup. Okay, thank you for your attention.